Okay, so I'm going to talk today from the using parallel computing with the Wolfram Compiler. I'll talk for about 40 or 45 minutes, and then we'll talk about things. I probably won't answer many questions when I'm talking, just to get through things. But yeah, okay, so I'm going to get going. So Wolfram Compiler. So it converts Wolfram language into native machine instructions that run. So there's no emulation or anything. It's directly generating machine code that runs on the metal, and it has lots of opportunities for developing new and innovative solutions. And it's very tightly integrated with Wolfram technology stack, and it's a key technology for implementing parallel functionality. So, outline of my talk, I'm going to have a little bit of background on the compiler, talk a little bit about issues for parallel computing. I'm going to talk about sort of multi-core computing and integration with OpenMP. And then if I have time, I'll talk a bit about some of what we've been doing for CUDA, with CUDA. Right, so this talk is not a general introduction to the compiler. There have been many talks, like recordings and things given, like at tech conferences. And I could give a general talk on the compiler, but that's not this talk. Right. So, but I'm just talk a little bit about it. So it's long-term project. It's built in the Wolfram language. It leverages, very modern compiler knowledge and technology, and it was first released in 2019, and it's been updated every version since, and there'll be a 13.3 update. So, as I said, it converts Wolfram language into native machine code. It has this sort of in-memory JIT compilation, but it also makes dynamic libraries, so you can sort of save. It has a static type inferencing mechanism, and it's a fast execution model for Wolfram language. It's an implementation layer for the Wolfram language. It integrates very tightly with Wolfram language interpreter and expressions. It can make standalone code, but that's not something that we really have worked on a lot, and we're enhancing it we have some, and we're doing more of this for the compiler to compile itself to make it faster. Right, so some of the obvious benefits of the compiler: you get faster execution. You also get a guarantee of correctness. So with the type annotations, if your program successfully type checks and compiles, it much more likely does what you want. When you write top-level Wolfram code, that is not the case. It fits very nicely with other code generation systems, and it's a nice way of leveraging new technologies. But it's also benefits, some also things, and this is people get very confused about, sadly, but it takes a high-level language specification and couples it to a low-level execution technology. It also lets you use Wolfram language in the workflow, so you can very easily, you're building solutions, you can use notebooks to visualize things or serialize things or make little plots to study how fast you're benchmarking your code or such like, and that's all pretty useful. Much harder with more traditional compiler systems. So for developers, a nice workflow is you can start out with interpreted code and then build up some compiled code, and then steadily build and test things interactively. And then when you start to get things that are looking good, you can move to deployment. And we have a new system that was added in 13.2 and is being this is the way to package, and they're called compiled components. It's a packaging system for the compiler. It integrates very nicely with the Packlet system and integrates nicely with the RI build system. So when you build a Packlet with compiled code written as a component, it's quite easy to build, turn that into libraries that can be integrated. And we've got quite a lot of experience of using this. So that's the deployment mechanism that we should be looking at. So just again, stress, people get very confused. They think they take their horrendous, muddled, tangled Wolfram language code and they just wrap function compile around it, and magically it runs faster. And that is not the case. It's not a magic solution where you magically wave some, or not yet anyway. So strengths of the compiler. So it integrates very tightly with the Wolfram language. And it's as Wolfram language development happens, the compiler gets updated. So a nice thing this is a benefit compared with other compiled solutions. It's one uniform compiler. And for people that work in the C code level, in any of our solutions, this is actually a negative, because when we build Mathematica, we build it with Clang and GCC and Visual Studio, and they all work slightly different. And it means that, we want to switch to a new standard, and then Visual Studio has a different way of doing this, and it's hard. It means we always have to work at the lowest, the bottom level. So that's and sometimes, I don't know what other in the kernel we've debated. Every now and then we debate switching, say, to Clang. I don't know what front end people might think about that, but that's a possible solution. So another thing that's kind of interesting is when you do the JIT compilation, it's actually building something that's optimized for the specific hardware that you're running on. So, like again, when we compile Mathematica, we're not compiling something that's optimized for your computer. We're building something that's going to run on, some legacy machine that's probably about 3 or 4 years old. So so that's, whereas JIT compilation is optimized for specific hardware. And all these processors, they have special instructions that get evolved and changed that can make, important advances in that can be quite advantageous. And it has a nice modern inferencing system. So weaknesses. Compilation is very slow. It's written in Wolfram language, so the code it produces is fast, but the compilation process itself is slow. So that's a negative. And we're working to address that by compiling itself. And we've had some successes with this. It's under development, so it's incredibly well tested. So it's probably the best tested, one of the best tested. We run millions, we run literally millions of tests daily, and the failure rate is tiny. So in the main test suite, we have, about a quarter of a million tests, and there's usually about 10 failures, which themselves are actually, tests that need to be. So that's good. It also has some raw edges that, in seeing failures and things that are being addressed as we go along. Right. So anyway, it's increasingly used in development. So one big use is the data structure library. That's all built from the compiler, but there's various numerical functions and things that have been enhanced and built with it. And it's also a nice way to integrate libraries. So it's much more efficient and easier to use than the old library link, which can have some very negative and expensive solutions. And actually, Christopher's working on yet a new way of library integration using foreign function interfaces that's even more convenient. Right. Anyway, so those are some of the uses. So that's my rattling through my talk. You may get through everything. So the traditional parallel computing that we've had for a long time, I think of it as parallel computing toolkit, but it's parallel functionality. And this is long-standing parallel functionality that we've had that works by launching multiple kernels, kernel engines, and it's pretty nice. It's good for working with heterogeneous networks. Now, since it's not sharing memory inside the things, and if it's going across a network or even across processes, there's some cost to interactions and there's some cost to moving data. But it's good for large-scale computations that can be replicated many times. And actually, the compiler is quite useful for this. So one of the nice features of the compiler is it supports cross. So in one invocation of the compiler, you can produce a function that has optimized code for, many different platforms, and that's actually quite useful for a heterogeneous network with the traditional compiler. But what I'm going to talk more about today is another form of parallel computing that is also important that we should have, and that's shared memory multiprocessor. So that's same processor, same process, same computer, shared a disk space, and it's using the multi-core nature of modern processors. And I'm going to call this multi-core parallelism, but maybe that's not always the best use. Now, we already use this quite a bit in the in Mathematica. So some of the libraries that we have, such as MKO, already make use of multi-core, and the runtime library, the RTL that we have, that also uses some parallel functionality through OpenMP. And we also have this old thread layer there's some parallel things built on top of that, and that's used in a few places. So that's some things like that. So just here are some issues that we might want to think about for multi-core computation. So it's like errors. We're running multiple threads, and we might have errors, and we want to think about how does, like we have the compiler works with exceptions in not all platforms, but some platforms, they're native exceptions. So we need to deal with threads. We need to think about propagating errors from worker threads to the main thread. We have a memory management system, and we need to make sure that that's thread safe, and we need to make sure that other things can be done in sort of thread safe, but particularly memory management. And we need, this is the thing that's so important, and people they think this is trivial, but it's absolutely not, is thinking very carefully about what patterns of code you want to build up. If you don't think about this, you end up with vast amounts of, tangled legacy organic code that's hard to deal with. And another big issue for multi-core computation is when you have legacy code, you have thread unsafe code, and that's often legacy code was just written, and it was never written with any idea of multi-core computation. And so that's a big problem. And that comes to a key point, is that the kernel is fundamentally thread unsafe. and kernel code cannot be called concurrently, and it seems to me an utter waste of time to try and fix that. I mean, I think we should make new code solutions that are thread safe and not put any effort into the kernel. Just deal with it as a sort of black box that's out there. The RTL, which is much more structured and carefully written, is much more hopeful, and I think it's reasonable to think many parts of it are thread safe, and I think that's more more feasible. Right. So, I just repeated the same thing. Right. So, slide that. So, in the RTL, there is this base thread layer for managing threads that forms an abstraction across P threads and Windows threads, and we can create threads and join them, and supports mutex and condition variables. But I don't think that is absolutely not something that parallel computation should ever use. It's much too low level, and if people try to make use of that, you know, it's going to go wrong. Now, the compiler provides bindings to these things, and the thread creation integrates quite well with the closures in the compiler. But like I said, this is just much too low level a layer to be working at, and it's easy to get wrong and make mistakes. And we don't want to use this for parallel computation. So I'm not going to talk about that. So what I'm going to talk about is a higher level system, and I'm going to talk first of all about OpenMP. So OpenMP is a popular multi-core programming system. The basic idea is there's a main thread that forks sort of multiple threads, and they can share data. And a typical way is you can use this sort of pragma markup in C, C++, and Fortran, and you might mark up, say, a parallel loop to look like something like this. So you have like your for loop, and this for loop could run in like you know, if this pragma was ignored, this for loop would still run. And we support a thing like this in the compiler. So we have a parallel do that's an OpenMP version of a parallel do. So it's not quite, has some similarities with a do loop, but it's not exactly the same. But that's the similarity with the thing that you just saw. Now, this parallel do is using the OpenMP runtime. So there's like the OpenMP runtime is quite easy to, you know, it's feasible to work with it, and it has a lot of, and this follows the OpenMP functionality quite closely. So the advantages with this of using OpenMP is it's very well supported on all sorts of different platforms, and it has a huge amount of functionality. It would be hard to compete with that and build up the same functionality. Would just be, you know, a huge amount of work. And there's open source implementations of OpenMP. So if you know about this, I mean, it's like fairly dense C++ code, but it's quite feasible to work with the open source implementations, and that's something that I do quite a bit to sort of understand. Look at the thing. Right. So anyway, here's just you know, so I'm not going to give lots of examples in this, but I can run. So here I'm giving a packed array. This is the sort of destructive operation you can do. I can get the data out. I can modify the data in a loop, and I can run this, and you know, it sort of runs like so. Or here's another version. I'm compiling. I'll compile the So here I've compiled the a version with parallel do, and the same thing is just like regular do. So they're both compiled versions, and let's see what happened there.
Sorry, is that modifying the argument in place?
Yes, yeah. This is I said that this is a destructive.
Okay.
I said it's a destructive operation, so you can do things like that
Okay.
in the compiler. So we get a nice you know, a nice parallel. You know, it breaks up the tasks, and you get a nice acceleration for that. I mean, it would be entirely feasible to create a new array and then fill that in. It's just that's not what this example did. So parallel do, the OpenMP, it has a couple of options, and it's going to have many more, but it's got one that says whether to execute in parallel or not, and one whether to catch exceptions. And so you can pass in, just need to keep a little eye on the time. Yeah, we're not doing too badly. So this one here, I've got parallel do, and I've got an option here that says whether you should run the loop in parallel or not. And let's make some data, and it's the same old boring data. And so here I said true, run in parallel, and here I say false, don't run in parallel. So it's faster to run like that in parallel. Also, another option is this, is whether exceptions should be caught. So in this operation, I'm doing an addition, and this addition is a validated, it's part of the arithmetic system. So it's a validated, and I'm saying it should catch the exception. And so the default behavior of catching exceptions, it just repropagates. So here I started, you know, I'm adding 10 to every element, so not a problem there. But here I'm doing this, and you know, at some point it overflows and we get a failure coming out of it. So that's and you can catch the exceptions yourself and have different behaviors if you wanted. But the key thing is it's catching the exceptions. If you don't catch the exception, then the exception mechanism will exit the process if it doesn't find something to catch the exception. We've got a bunch of you know, support functions. So we've got and these things are useful. So there's a thing you get like the number of threads, and you can get an index of the current thread. And part of the specification is that the index goes from like 0 up to the number of threads, 0 being the main thread. So you can use this index. You can make like a workspace arrays based upon the number of threads, and then use the thread index to index into it. And we've got this critical section thing, which can be useful. You know, only one thread can enter the critical section at any one time. Now, on top of this parallel do, we've built a bunch of other constructs. So this is probably the most useful one.
Sorry, Tom.
Yes.
Can I ask a question?
Yes.
So in the previous slide, you showed that OpenMP backtick global number of threads.
Yes.
What's the relationship between that and system option, parallel options?
Well, they're probably going to be quite similar because they're both OpenMP driven. But this is, you put this into compiled code. Okay.
Okay, so that is just specific to the compiler and doesn't.
This is an API function for getting it. It's a bit cumbersome to have to go through system options. Okay, let's talk about that. That's a very micro question. Let's talk about that later if that's still an issue. Right. So So this is a MapReduce type function. So we don't have a MapReduce in Mathematica, in Wolfram language, because we have fold. So fold is like super useful. I love fold. It's my favorite function. and you iterate, functionally iterate over elements in some sequence, but it takes a workspace that it propagates through that, or an accumulated result that it propagates through. And that's fine when it runs sequentially. But the problem is, if you want to break the thing up, you actually need to have two different. So you need something like, a MapReduce, where you're applying another function to each element. And the reason why it's useful is that you can break up. So in one thread, for example, you could produce a list of lots of mapping things and apply the map function to every element, and then you could reduce them all, maybe in the main worker, maybe in different things. And you might run the reduce function multiple times in different threads. And this is what makes MapReduce suitable for parallel computation. So we built let's just see this, a parallel MapReduce, so OpenMP. This is built on top of the parallel do, and so it's kind of like, there we go. So I'm generating random numbers, and I'm basically counting everything that's equal to a value. I'm going to add all those up. So this is counting basically, and it's kind of like a lot faster. There we go. It's a lot faster than and this is a built-in. This isn't, I haven't put, this count, it's like a built-in function. So this is really a lot faster. So right. We have a parallel table. Let's see, parallel table. Yeah, let's look at parallel table. And this thing here, I mean, this is like range really. And I can run this. And here, piece of timing. Now, so here I'm just replicating like range, and range is implemented in the RTL. It also uses OpenMP. So this is, it compares well, the built-in thing is pretty good. So right now, and we have a parallel map. And go, and blah, blah. And we can do, what can we do here? Oh, this is, yeah, it's a lot faster to do things in the compiler and be parallel. So now, yet another thing I'm going to talk about is, these are some of the issues you face in parallel computation. So this is a common type of, you want to you have some workspace, and I want to increment an element in it. So what this becomes in lower level instructions are, you extract the value, you compute the new value, and then you assign the new value back into the buffer. So if you do this in multiple threads, if you have the same index, then what you hope is, what's going to happen is this. You do one increment, and then the next thread does the other increment. But, whoops, what might happen? These things might not be quite so cooperative. So you might get one extraction, and oops, the other extraction happens. This is a problem. You're going to have read, write, and you'll get the wrong result. So a solution to this that we've just added to the compiler is an atomic update function. So, and this uses intrinsics in the compiler. And so this is like an update of an array so it's like this array, this position, run plus, and that's the other argument of the plus, and this is guaranteed to run atomically. It's guaranteed it will always be read, write, and it runs much faster than locking a mutex. But it only works for a few operations like plus, subtract, and such like. But this is a nice big advantage of using our own compiler, is it's kind of handy for reaching intrinsics and such like. This atomic updating is quite useful for memory management. So the core memory management system, like expressions, or is based upon reference counting, and we are currently switching to do atomic updating for reference counting, which seems like it works, but we need to do more, a bit more benchmarking on this. But looking at the expression functionality, there's a whole load of places for like setting content codes and things like that could also use atomics and start, make them more thread safe. So that's kind of interesting. So just talk a little bit about code patterns. So important to have a careful layering to avoid organic messes, which we have tons of. And one idea here is that any algorithm or technique to develop a serial implementation and then use that in a parallel implementation. And this is like we want to have parallel copy. So what you would do is, first of all, write a slightly simplified a serial implementation of a copy. So this is this thing here, it does some shifting, and then it's going to call this thing here, which is basically memcopy, which is also like a super efficient way to copy data. And then here's the parallel version. So the parallel version goes outside of this, and it checks some parallel threshold. If it doesn't meet the threshold, it just calls the serial version. But what's nice is in the parallel version, it breaks things down into blocks, and it does the serial version on each block. So this is a nice layering and structuring of the code. So you have the serial version driven by a parallel version. And this is a key. If you don't work to strive to get these things, you end up with a mess. Now, so OpenMP supports in the what we've achieved. So we have pretty functional access to the OpenMP runtime. We have a workhorse of this parallel do, and we have thread safe exceptions. So where we have not that we're working on is to add different schedules. So again, I'm not going to go into the detail, but there's different ways of whether you just break the whole loop up into, number of threads into separate loops, or you do things differently. We just do what's known as static. OpenMP has other paradigms like tasks. We need to finalize memory management. This is being sort of built out, and we need some careful work to do with kernel calls to make sure that they're very carefully synchronized. So if you call the kernel multiple threads, it crashes. So it's got to be. But what we have is really quite functional. So that's all quite handy. Okay, I've got a little bit of time, so I shall just switch gears and talk about what we've been doing with CUDA and such like. So this is like fun and games type of things. So CUDA is a parallel computing architecture that it has a lot of software tools and APIs, and it runs on NVidia GPUs. So it's only one platform. Since it's NVIDIA GPUs, it doesn't run on the Mac. There's other platforms, but CUDA is by far the leading one and the most, sort of such like. So NVIDIA GPUs, they can be used in this sort of massively parallel. GPU can have hundreds or thousands of cores, and the cores themselves typically run in blocks of like, and this is often handled automatically for you, but they'll run in blocks of 32 or more. And each block, the cores run completely synchronized. So it's like they have the same clock. So on my Intel Mac here, I've got like, a bunch of different CPUs, but each CPU has its own clock. And sometimes you get, by design, different CPUs are different, clock speeds, but the GPUs, they all have their own, they run synchronized. And that's something that algorithms can exploit. They have their own memory system. It is expensive to move data from the CPU to the GPU, and it's all very different to multi-core CPUs. So we've had a long-standing toolkit, CUDA-Link, for working with GPU. The CUDA, it's quite low level, but we're building it out. And we're building all this new thing with the compiler. So it's based upon using libraries that CUDA provide, that NVidia provide, but also using the compiler pipeline to generate CUDA code. And this will be a new generation of CUDA-Link, or I'm not quite sure how this will be packaged up in the end. So let's just come and see. I think I've got another notebook here. And let's have a look at this. So some of the CUDA support, it's all a work in progress. And it's not been properly designed yet, but it's quite useful. It's built with the compiler, but actually a lot of the time you don't type compiler commands in it. The top level is just things that drive the compiler. So we have nice ways of working with data on the GPU. You can declare something to be a CUDA vector, and then you can extract it to get, the underlying numeric array. You can get CUDA deck, you can get information and types and lengths. So a key thing is it integrates with the memory management system of expressions. So when the CUDA vector is no longer used, the memory gets collected, and that includes this, expression handle to it. So when this, this gets cleared, tidies the thing up. So in addition to CUDA vector, there's a CUDA matrix, a sparse vector, and a sparse matrix. And the atomic data can be various integer float and complex float values. So you've got various things to work with the CUDA data, part extraction, various, sort of BLAS and Fourier type. These are all built with NVIDIA CUDA libraries. So these are new things. So now we're developing things like a version of table, but it generates a CUDA vector. So what this is going to do is it compiles the body of this into the code, the PTX code that runs on the, that runs on the machine. It uses a cache, so sometimes it can avoid. So if you want to tweak, the lengths or something, it doesn't really need to do that. And then it runs this kernel on an input data and fills it in. So this has some limitations. So you can't call the kernel, you can't call integrate or desolve, and it works with a limited set of mathematical functions, but often you compile things and build up work, and we're still developing good feedback and error messages when this comes up. We have a CUDA map, so when you take a CUDA vector, you can apply a function over the elements and get a new CUDA vector. We have a map reduce, so these things start to run, sort of astonishingly fast. And this is kind of interesting. So this is the lowest level, so you can actually write your own CUDA kernel. So these things start to look, like it's much nicer to write something like MapReduce with Wolfram lambda functions. And in CUDA code, you have to write all sorts of strange things, but you can do this. So you can create a kernel, and then you can do things like compile it into a CUDA kernel object. So this is something a little bit like a data structure, but it contains a serialized form of the, I think there's some extra lines into this, but this is like this low-level language that you don't really want to program in. in the PTX. This is the language that actually executes. So we've taken a Wolfram language function and generated something that'll execute on the kernel, and then you would feed it into a run kernel with the right number of arguments, and it runs. And everything that we do with our CUDA is built up from this. And I think that's the end of, that's the end of the CUDA stuff. Let's come back. There's my, oops. So, I mean, the algorithms that you run on CUDA are completely different. It's simply not realistic just to take anything other than very high level descriptions. Maybe a Wolfram language description might be high enough level, but it's not realistic to take anything, you know, algorithms and just like recompile them on CUDA. They are just different. Right, fine. So come to the end, we can have a talk, or we can all go off and do other things. So I was giving a run through of the compiler and some of the directions that we're thinking about for parallel support. I was saying how the predominant idea is using the OpenMP runtime and using some of the ideas from OpenMP. I did give a preview of new CUDA support, and just to say there is a compiler manual, and that's on the Packlet, and I've been doing some work to update this, and this has some sort of, you know, it's kind of a tutorial introduction to the compiler. So that's the end of my stuff. So I don't know if anybody wants to ask questions or some such.
Tom, the old compiler
had
an ability to automatically parallelize.
It was super limited. So you didn't put things inside the function to parallelize. It was very limited. So you could, you know, it was a little bit like sort of listing over the, you know, being listable over the input data in parallel. But it was nothing like, I mean, it was very primitive. So yeah.
Does the new compiler have the ability to automatically parallelize, or do you have to be explicitly use OMP and things like that?
Well, I think that's, well, I mean, in the old compiler, you had to set options and things, so it wasn't, it just, you know, so it, you know, it wasn't completely, it wasn't automatic, it just worked at the function level. So the function itself would run over multiple data. So I mean, I don't think it's impossible to think about, you know, sort of automatically parallelizing. But and again, the compiler can, it's a compiler that we control, so we kind of know what the code is doing, so we can analyze the code for side effects and problems and make choices like that. So that's, but the core thing that I'm thinking about now is to build up a robust set of primitives that would allow parallel algorithms to be developed. That's what I'm thinking now.
So have you looked at any other models than NVIDIA's for GPUs?
Sure, they are. Oh, absolutely, tons of them. They're much. There's much less. They just do an awful lot less. And the CUDA support also is very advantageous because it works through LLVM. So the underlying technology of the compiler is LLVM. So that means generating the PTX can be done, you know, very conveniently. For other things, and I thought you could generate, you know, I thought about generating shader languages and things like that. It would need a new back end to be written. So that would be interesting. But I think we'll get, you know, in our budget of development resources, I think making a good CUDA solution we'll get more functionality more, more quickly, in my opinion.
So there are other frameworks like Intel's One API
Yep.
that are trying to unify CPU, GPU, and other accelerator support.
Right. Every
Question
time
is so far,
every time I look at these things, it's not
quite there.
It's a long way, more than not quite. It's a long way from being there. So, I mean, I look at these things and then I look at CUDA and see what we can do. I mean, we can make real progress with CUDA. So in ways that are, it's not so, not so easy with these other things. I mean, there are these libraries like Magma and things, and we looked at those, but it's just, I mean, we can do so much more with CUDA. So
I think the advantage is that most people don't have NVIDIA GPUs, first of all. So the advantages of these other ones is that it can run on the machines that people actually have.
No, I understand all that. But on the other hand, for serious HPC uses, people are going to buy specialized hardware anyway, and they're going to be willing to I mean, the NVIDIA is, it's not unused. I mean, it's quite dominant. So, and everything you're saying, especially if you have a Mac, it's a nuisance, because you can't, there's no solutions for a Mac. But you've got to buy a Windows machine or a Linux machine. So, but CUDA is very dominant. If there was another dominant thing, then we'd think about it. So it's absolutely in the roadmap to work on these other things. It's just that we can make progress much faster with CUDA.
Well, thank you very much, Tom.
Sure.
It's a great update.